I'm going to introduce what I'm going to call the cotangent technique. It is essentially a generalization of similar triangles. Here, I'll explain what I mean. Suppose that you have a triangle in which you have to prove that this angle alpha equals this angle alpha prime. You're solving the problem and you're trying to fit those angles into similar triangles. Maybe you fit this angle in this triangle and you fit this angle in this triangle. And you're trying to find such triangles for which this angle gamma equals this angle gamma prime, and for which b divided by a equals b prime divided by a prime. If these two conditions are satisfied, gamma equals gamma prime, and b divided by a equals b prime divided by a prime, then you can claim that the triangles are similar, and hence that alpha equals alpha prime. With the cotangent technique, you can prove that angle alpha equals angle alpha prime, even if angle gamma does not equal angle gamma prime, and even if b divided by a is not equal to b prime divided by a prime. The only thing we need to know about these triangles is we need to know the values of the sine and cosine of gamma and the sine and cosine of gamma prime, and we need to know the value of b divided by a, and we need to know the value of b prime divided by a prime. If we know these values, we can calculate the cotangent of alpha and cotangent of alpha prime, and hence prove that the two angles are equal. If this angle is alpha and this angle is gamma, it follows that this angle is 180 minus alpha minus gamma. And now we can apply the law of sines for this triangle, and we get that b divided by a equals the sine of this angle divided by the sine of this angle. So sine of 180 minus alpha minus gamma divided by sine of alpha. But we know that sine of 180 minus alpha minus gamma equals sine of alpha minus gamma. And so we get this expression. And now we can apply the formula for sine of alpha plus gamma, and get that it equals sine of alpha cosine of gamma plus cosine of alpha sine of gamma. Now the sine of alpha cancels out here, and cosine of alpha divided by sine of alpha equals cotangent of alpha. And so we can rewrite this expression like that. From here, we can express the cotangent of alpha with respect to the other quantities, and we get b divided by a from here, minus cosine of gamma from here, divided by sine of gamma from here, and this equals cotangent of alpha. We can rewrite this expression like that also, b minus a cosine of gamma divided by a sine of gamma. Now you can see what I was talking about. If we have a triangle in which we know the ratio b divided by a, and we know the sine and the cosine of the angle gamma, then we can calculate the cotangent of alpha by using this formula. If we need to prove that this angle alpha equals this angle alpha prime, we just need to put them in triangles for which b divided by a is known, b prime divided by a prime is known, and the sines and cosines of the angles gamma and gamma prime are known. We're going to get this value for cotangent alpha and this value for cotangent alpha prime. So we just need to prove that this expression equals this expression, and it would follow that cotangent alpha equals cotangent alpha prime. If this is the unit circle, we know that this here is the cotangent axis. Suppose that both angles alpha and alpha prime are between 0 and 180 degrees, which are most angles that we work with in geometry problems. Then suppose that we proved that cotangent alpha equals cotangent alpha prime. Is it necessarily true that alpha equals alpha prime? Oh yes, because you see, it's impossible to have two different angles between 0 and 180 degrees that give the same value for the cotangent. Suppose that the cotangent of alpha comes here, corresponds to this point on the cotangent axis, and then cotangent alpha prime corresponds to the same point here, then both alpha and alpha prime must equal this angle here. And if cotangent of alpha corresponds to this point here, and cotangent of alpha prime also corresponds to this point here, then both alpha and alpha prime must correspond to this angle here, because both angles are between 0 and 180 degrees, so none of them could go, for example, here or here. In conclusion, if cotangent alpha equals cotangent alpha prime, then alpha equals alpha prime. Here is a short, nice proof of the cotangent technique. Drop an altitude like this, then from this right angle triangle with angle gamma here and hypotenuse A, we get that this side is A cosine of gamma and this side is A sine of gamma. And since this whole side is B, then this small side here is B minus A cosine of gamma. And therefore, cotangent of alpha equals this divided by this in this right angle triangle, which is B minus A cosine gamma divided by A sine gamma. So we get this, which could be rewritten like that. Of course, this proof only works for acute angled triangles. This is the optional problem. We have a triangle, and this here is its circumcircle, and this point is the midpoint of this large arc in the circle. So from this point to this point. This point is the incenter of the triangle, and this point is the midpoint of this side of the triangle. We need to prove that this angle equals this angle. And here's the solution. Let the angles of the triangle be alpha, beta, and gamma, and let this side be C. Then because this is the midpoint of this side, this length is C divided by 2. And because this is the incenter of the triangle, we know that this and this are the internal bisectors of this angle and this angle. And so this angle equals gamma over 2, and this angle equals beta over 2. Since this is the midpoint of this arc, it follows that this point lies on the perpendicular bisector of this segment, but it also lies on the circumcircle. And we know that the external angle bisector of this angle, which is this line, intersects the circumcircle at a point that lies on the perpendicular bisector of this side. Therefore, this line is exactly the external angle bisector of this angle. And therefore, this and this are perpendicular lines because the internal bisector and the external bisector in a triangle are always perpendicular to one another. We know that this quadrilateral here is cyclic, and therefore the sum of this angle and this angle here is 180 degrees. But this angle is 90 plus gamma over 2, and therefore this angle must be 90 minus gamma over 2. And this angle is alpha, so this angle must be 90 minus gamma over 2 minus alpha. But you can see that 90 minus gamma over 2 minus alpha equals beta minus alpha over 2. Just replace the 90 with alpha over 2 plus beta over 2 plus gamma over 2, and you're going to get this. And therefore, this angle is beta minus alpha over 2. From the law of sines, we get that this segment is 2r times the sine of this angle, beta minus alpha over 2, since the circumradius of this triangle is the same as the radius of this circle. We also know that this distance from the vertex of the triangle to the incenter is 4 times r sine of alpha over 2 sine of beta over 2. And this distance here is 4 times r sine of alpha over 2 sine of gamma over 2. Do you see what happened? We managed to put both this angle and this angle in triangles for which, for example, this triangle, we know this angle is beta over 2, and we know this side and we know this side. Therefore, by using the cotangent technique, we can find the cotangent of this green angle. And this green angle, we put it in this right angle triangle, for which we know the sine and the cosine of this angle, 90 degrees, and we know the length of this side and the length of this side, and therefore we can find the cotangent of this angle. Let's call this angle psi 1 and this angle psi 2. Cotangent of psi 2, because of this right angle triangle, equals this length divided by this length. So 2r sine of beta minus alpha divided by 2, divided by 4r sine of alpha over 2 sine of beta over 2. We can cancel out the 2r with the 4r here, and then we get sine of beta minus alpha over 2 divided by 2 times sine alpha over 2 sine beta over 2. For cotangent of psi 1, we know that it equals c divided by 2 divided by this side, 4r sine alpha over 2 sine gamma over 2, which is written here, and then minus cosine of beta over 2 divided by sine of beta over 2. We can replace c with 2 times r sine of gamma, and we get this expression. We can cancel out the 2r here, and we can substitute sine gamma with 2 times sine gamma over 2 cosine gamma over 2. And then we can cancel out sine of gamma over 2 and sine of gamma over 2, and one of the 2's here, and then we get cosine of gamma over 2 divided by 2 sine of alpha over 2 minus cosine beta over 2 divided by sine of beta over 2. And now we can substitute cosine of gamma over 2 with sine of alpha plus beta over 2, because we know that gamma over 2 plus alpha over 2 plus beta over 2 equals 90 degrees, and we can rewrite the expression like that. And now we can apply the formula for sine of alpha over 2 plus beta over 2, and then we get that sine of alpha over 2 plus beta over 2 equals sine of alpha over 2 cosine beta over 2 plus cosine alpha over 2 sine of beta over 2. And now we can cancel out one of the terms here, sine alpha over 2 cosine beta over 2, with this term, and then we get this expression here. But this numerator is actually a formula. A formula, sine times cosine minus sine times cosine. This is sine of beta over 2 minus alpha over 2. So in conclusion, cotangent of psi 1 equals sine of beta minus alpha over 2 divided by 2 times sine alpha over 2 sine beta over 2. And now let's see what we've got for cotangent of psi 2. You can see that we got exactly the same expression, sine of beta minus alpha over 2 over 2 sine alpha over 2 sine beta over 2, which is exactly the same as here. And therefore, cotangent of psi 2 equals cotangent of psi 1, and so psi 2 must equal psi 1 as desired.